Autonomous Vehicle Science Lecture Series, Number 2. Line Tracking, from MotionLab. The line tracking geometric motion, GM, is the second among the 5 geometric motions, GMs. 1. We define a line tracking motion by a line L and a gain G, greater than 0. 2. We define a line L as a position P and a direction θ, L equals P, θ equals x, y, θ. 3. The vehicle exponentially converges to line L. In the following 3 line tracking motions, line L equals 0, 0, 0, the x-axis in the positive direction. The vehicle's initial frame is P0, θ0, equals 0, 50, 0. Line tracking motion, gain equals 0.025. The gain parameter G works as follows. A larger gain G makes a sharper turn spatially. A smaller gain G makes a less sharp turn spatially. With a smaller gain 0.025, this motion is less sharp. Line tracking motion, gain equals 0.04. This motion uses a gain of 0.04 and is sharper. Line tracking motion, gain equals 0.08. This motion uses a gain of 0.08 and is the sharpest among the 3. The line tracking GM is the most frequently used in SWAN programming. Effect of gain in line tracking. This diagram demonstrates the effect of using 3 distinct gains, 0.025, 0.04, and 0.08. In this star motion, the vehicle's initial frame, position and direction, is Q0 equals minus 250, 0. Initially, the vehicle tracks a line L equals minus 250, 0. After tracking a line L1, the next line L2 is created by composing L1 and a transformation, 400, 0, minus 4 pi over 5, equals 400, 0, minus 144. Eventually, the vehicle tracks 6 lines, producing a 5-point star. The gain G determines the size of the turning. The neutral switching rule controls the precise position where each right turn of minus 4 pi over 5 starts. The same data structure, XX, YY, TT, means 3 distinct geometrical items. We use the same data structure, XX, YY, TT, to represent 3 geometric items, frame, line, or transformation. In this star motion, minus 250, 0, means an initial frame of the vehicle. Minus 250, 0, is a directed line to track. 400, 0, minus 4 pi over 5, is a transformation. This 3-way interpretation of the data structure is extremely beneficial in math-mind arithmetic. Star motion, 3. SWAN vehicle executes the same star motion here. Andrew partially obstructs its motion, but its trajectory does not change. Gain medley. This is a compound motion, repeating square motions with right angle, pi over 2, turns. The gain G controls the roundness or sharpness of each turning. We use distinct gains at each cycle in this gain medley motion with gains of 1/5, 1/10, 1/15, 1/20, 1/25, and 1/30, respectively. As the gain decreases at each cycle, the corners of trajectories grow bigger. The shapes at corners are similar to each other. Nonlinear homogeneous differential equation. To find out the line tracking algorithm, we have to solve a nonlinear homogeneous differential equation. We want to achieve asymptotic stability of zero equilibrium solution of the dynamic equation by a proper choice of parameters. To study the stability properties of the zero solution, we refer to Lyapunov stability theories. We use linearization and eigenvalues to obtain solutions. In this process, we select a proper value of a parameter gain. Swan vehicle hugs a structure. Swan first scans the left side object with left side sonars to get a sequence of target points. Applying the regression analysis to the point set in real time, MathMind obtains line segments. To hug this structure, Swan vehicle then tracks those line segments with the line tracking GM. This motion is stable because the regression analysis produces precise lines based on numerous target points. Staircase. This is a compound motion consisting of 16 left and 12 right turns. Then, as a net effect, the vehicle makes a counterclockwise turn of 2 pi. Notice the precise geometric formation and rigorous execution of the neutral switching rule. Polygon medley. This motion creates an equilateral triangle, square, regular pentagon, and hexagon in this order. For each, its counterclockwise and clockwise polygons are drawn. Each edge in an n-gon is systematically created from the previous edge by the 2D composition operation. The transformation angle is +2/n if the polygon is counterclockwise, and -2/n if the polygon is clockwise. We use the neutral switching rule in switching from one edge to the next. Obstacle following. If an object has a convex envelope, a vehicle can draw only one tangent line on either side, left and right. By repeating these processes, the vehicle can hug the convex object by successively tracking tangent lines drawn from the vehicle to the object envelope. The vehicle can hug an arbitrary convex object with real-time tangent updating. Obstacle avoidance and following. 1. If an object has a concave envelope, the vehicle may find more than one tangent line on either side. In such a case, the vehicle can hug the object by successively tracking the shorter tangent line first. Andrew was never scared by the close encounter with the vehicle. Obstacle avoidance and following. 2. Using this slightly modified algorithm, the Swan vehicle successfully hugs even concave objects. Everyone is aware of what the vehicle is doing and what it will do next. An MM car acquires trust from people. When a car installs MathMind, we will experience the following. MathMind selects the best fitting GMA in the current situation, and the motion looks natural. Hypothesis K2. Therefore, people intuitively understand the car motion's purpose, what the car is doing, and what it will do next, without verbal explanations. Andrew exactly experienced this with the Swan. Therefore, the passenger and pedestrians do not see the car as a brainless, heartless cruising machine, but as something predictable and trustworthy, as is currently experienced with human drivers. Gate bisector tracking 1. In this motion, swan vehicle's sonars sense the two cans' positions, left and right. Then, the vehicle computes their bisector, which the vehicle tracks. Racetrack bisector tracking 2. In this motion, the vehicle executes the same sensing and same motion as the previous motion. Even though the surroundings are not well structured, the vehicle's bisector tracking is robust. We deliver the best motion creation capacity for self-driving cars. MotionLab possesses sensor-independent and vehicle hardware-independent motion creation technology for self-driving cars. If your company is interested in our licensing offer of the MathMind technology, please visit our site motionlab.info with DreamCar as the password and click the Contact button.